Next speaker is Chad Hall, who will tell us about the ALMA revolution.
All right. Yes. Yeah, sure. You can put on a tie if you want. Pointing this way, yeah. All right. I will tell you about a very specific part of the ALMA revolution, the class 0 protostellar polarization part of it, which is Michael very nicely introduced. Thanks again for introducing all of, basically more than half of the talks in the next today, which is fantastic. So I'm very happy to be here, and before I give my typical short introduction to magnetized star formation, I want to give an introduction to Carl and Dick here. I found a nice vintage photo of Dick with pixelated words here underneath from the NCSA. I just want to say that both of these gentlemen, so Dick Planbeck was my main advisor in Berkeley, but I got a lot of fantastic help from many people, including Dick and Carl. And Dick in particular was helped a lot with the tadpole survey, which is that Michael just showed a few objects from our survey. Basically, we executed this massive project, and Dick's criticisms and suggestions and analyses were always very welcome. So thanks a lot for that. And to Carl, who is one of my co-advisors at Berkeley, I appreciated all of your help with the polarization, and specifically your occasional bluntness, where you just wanted me to do something. And so I think at one point, this may be slightly exaggerated, but I think you said, if you don't debias your polarization maps correctly, I will not sign your thesis.
I think I did say that.
I think you did. Thus was born the Python code that I've actually suggested to people when I've been refereeing their papers. So I now debias polarization correctly, and my thesis was signed by Carl, as well as by two other folks in this room, Dick and Chris. So thank you again for all of the inspiration and motivation and very sage help throughout my PhD and beyond. So cheers, gentlemen, and a quick, very brief introduction. I say up here, see, I wrote this talk before we had the various invigorating discussions here, that magnetic fields are important on large scales. Juan Soler will shed more light on this later today. I'm now nervous about saying that because there are many different opinions in this room, and work and opinions are now progressing about whether this really means that the magnetic fields are actually important dynamically, but for the sake of getting through the talk, I will simply say that. These are magnetic field orientations from background starlight polarization in a cloud that is about 10 parsecs long, much larger than what I normally look at with an interferometer. But it has been said that the fact that the magnetic field is perpendicular to the spine of these clouds, and that magnetic fields, when strong enough, tend to help guide interstellar material form these filamentary structures, that the magnetic fields are important on those scales. And just to show more recent data as well as a different wavelength of data, instead of optical absorption, now we're looking at millimeter emission from the Planck data. You see the beautiful total intensity emission overlaying it there. And then if you memorize the magnetic field orientations here, you overplot the Planck polarization map, you can see that they're consistent, and you can see not only polarization on top of the brightest emission, but everywhere else as well in the more rarefied stuff around the dense objects. So I'll leave this again to Juan to talk a little bit more about, but basically on large scales, magnetic fields seem to be important, but what about on small scales? So we have here an artist's rendition of a forming star. Maybe you've got a 100 AU disk, you've got a protostar in the middle, the outflow, and then most importantly, you have these little magnetic fields, these blue lines, that are thought to pinch in to make an hourglass, which is what Michael showed. Again, we only see that occasionally, but we do sometimes see it, suggesting that the gravity is actually pinching these initially poloidal fields. And so we want to know if on these scales magnetic fields are still important as we purport that they are on larger scales. And so a little tour of magnetized protostellar envelopes. The envelope is, say, 1,000 AU, 500 AU. I gave it that name for lack of a better word because that was the real bread and butter physical scale that CARMA and the SMA could get with the sensitivity that they had. Of course, now with ALMA, things are different, and we're going to smaller scales. But just a couple more objects to add to what Giuseppe Michel just showed us. So this is L1157. This is one of the very few hourglass sources we saw in our CARMA survey of magnetic fields in these class 0 protostars. So you have the hourglass here. It's nicely lined up with the outflow, and if you do the Carl Heiles blink comparator, you see that it really does look like the artist's rendition. And that was the second object we looked at. The first one was IRAS 4A, which also had an hourglass, and then basically nothing else did after that. So go surveys. So the results, and this is what I was answering the question about before. Where the gentleman who asked the question is back here. Basically, the results of the tadpole survey are kind of, this is an emblematic plot. You have these two protostellar cores 10 arc seconds apart. The outflows are kind of parallel, you know, when you project in the plane of the sky. The magnetic fields are basically perpendicular, and all told, the outflows in the magnetic fields are random. And we, as I said in the answer to my question before, we confirmed that with basic Monte Carlo simulations of pairs of vectors in 3 space. And so the conclusion that we drew when looking, again, you have to remember that outflows are launched on very small scales, maybe 1/10 of an AU or an AU in a disk wind. The outflows on those scales, as detected in molecular lines here, and magnetic fields looked at on scales detectable by CARMA and the SMA, so on 1,000 or 500 AU scales, they're randomly aligned, suggesting that the magnetic field on those scales, and on much larger scales, sometimes you see that the magnetic field is dragged in and consistent from hundreds of parsec scales all the way down to hundredths of parsec scales, that magnetic field does not play a substantial role in actually setting the angular momentum of the disk, the protostar, and the outflow at the smallest scales. So that was what we concluded early on. Now, as good astronomers do, we continued with the high-resolution observations now that the ALMA polarization system is working. And this is a picture that I took when I was very, very lucky to be able to go up to the high site at sunset, which is technically not allowed. It was a great irony because we were kind of not grandfathered in, but we were allowed to go along with a newspaper reporter from, I think, Colombia. And he didn't actually pass the physical, so he couldn't go up to take the pictures, but we got to go up anyway. So it was a truly special experience, one that I will probably not be able to do again. And using this instrument, I'm just going to go straight to the data. So these are the 850 microns. This is band 7 for those of you who use ALMA, dust emission data. And I will now overlay here the CARMA data. So the background overlay, these are the CARMA contours of the total intensity Stokes eye dust emission. You have here the magnetic field lines that you can just see very lightly. And you can see how much unbelievable structure ALMA pulls out. So this is a 2-point mosaic. The noise level is, it sounds like a noise level that you would get from VLA data, and it's from ALMA. I mean, it's really unbelievable. And you can see in this one here, you're recovering probably this X-shaped heated outflow cavity. Down here, I'll show you in better detail, it's complete chaos. Here, you're actually recovering what appears to be a very dense inner spine of this filament that we saw very clearly with CARMA. You resolve out a lot of it because, of course, with an interferometer, you can pick the spatial scales you look at. And with the ALMA data, it's a 0.3 arcsecond resolution, factor of 10 higher resolution than our CARMA data, but ALMA is very sensitive on multiple scales, and so we even recovered some of this filament. So there's all kinds of work to be done just with these total intensity data. But I will now, of course, show you the polarization data from cycle 2 observations. So this is the first one. This is Serpens embedded 8 north. These are magnetic field orientations. You see this X-shaped outflow thing, and after reprocessing the data about 100 times, I was able to calibrate a little bit better and pull out this little piece here. So you see that if you squint and kind of average this, you get the east-west orientation that you see in the CARMA data right here. So that's all consistent. So CARMA works, the SMA worked, ALMA works, it's all good. You know, this is all consistent. But you also see that right on the peak, something different's happening. And if you truly are a believer in the hourglass, then you could see that this is kind of a feeble other portion of the hourglass here, where you have this pinch in the middle, because this orientation right here in the middle is not exactly perpendicular to the outflow. So it's not necessarily toroidal wrapping, it's not necessarily scattering, though it could be, I don't really know. But it could be a little piece of an hourglass here. But the main question here that remains to be answered is why, when you have this beautifully symmetric X-shaped dust structure, why do you only get polarization very strongly along one axis there and really just barely along the other one? So is it being pulled in from larger scales? As Giuseppe Michel showed in one of his plots on Serpens, the overall field, a factor of 1,000 larger than this, is east-west. Is that just a coincidence? I'm not sure. So that's number one. Number two is where chaos truly reigns. Serpens embedded 8. This is complete madness. So we're only beginning now to figure out what might be going on here. You can also see that depending on which direction you go from here, when you get onto the top, you get a little kink. Again, that orientation right there is not perfectly perpendicular to the outflow. In the case before with the X shape, it looked like the outflow was actually having some effect, maybe compressing the magnetic fields along the outflow cavity, something like that. But here, the outflow doesn't seem to be having any effect whatsoever, except maybe pulling the fields in this direction. The thing that I really want to highlight here is that we think maybe this is a magnetized accretion flow. People have thought that perhaps if you have infall along filamentary structures to feed material onto the central disk and protostar, you will have magnetic fields maybe dragged along that filament, or perhaps they're strong enough to guide the material. That's the chicken and egg question we've been asking this entire conference. So this filamentary structure in the Stokes eye and also in the polarization where it happens to follow it is what we're really focusing on with this object. And just for completeness, I want to show the third object. I don't normally in this talk because it's kind of far away and is a different object, but just to show all of you interested parties all of the polarization data we have, here's the CARMA data toward Serpens SMM1, a higher mass protostar that Josette Miquel focused on. And here is the PowerPoint science to scale ALMA image. Now we zoom in, and here are the ALMA data, and I'm just going to flash a whole bunch of independent questions about this. So this is basically a 1 Jansky disk, which is completely insane for those of you who work in Jansky units. And here's the outflow. We see, this is what Alyssa alluded to, saying that maybe on small scales now everything actually is aligned, and all the theories were right to begin with, that magnetic fields and outflows truly are aligned. So here you see that at the smallest scales, the magnetic field is indeed perfectly aligned with the outflow. You get all kinds of other things too. You have the fact that here there's this bright blob going north-south, which very much dominates the signal when you do beam smearing. So with the CARMA data, I think a big effect, and probably with the SMA data as well, a big effect is the fact that the synthesized beam, or the resolution element, is just too big. You're smearing out a lot of the structure, and so there actually is kind of a symmetric perpendicular structure along the walls of an outflow cavity here that we can resolve with ALMA, but with CARMA, the resolution simply wasn't good enough, and we were biased by the part that was brighter. We were biased very heavily by this. This was like 30 sigma detection in CARMA, and this was maybe a 4 sigma detection. So beam smearing effects are going to be important as we look through the various objects that have been mapped at lower resolution. There's a high velocity outflow piercing this hole. This hole is real. There's a 100 kilometer per second outflow that we just wrote a paper on. There's also a lower velocity outflow that may be compressing magnetic fields along the cavity, or maybe these are 2 separate components that have nothing to do with each other. That's not yet confirmed. And again, just to echo what Josette Miquel said, this could potentially be scattering. If you were to take these magnetic field vectors and then rotate them back to where they should be for a scattering, or for the polarization pattern, which is what you would get from scattering, you would get this kind of circular pattern here. So many, many questions posed, some answered, many more posed. Just to go back to this, the Serpens embedded 8 with the filament, we're trying to tackle this accretion flow idea, and I just want to very briefly highlight some simulations that Phil Motes, who's in the audience somewhere, what he's going to show us later. So just to show you, to scale the state-of-the-art simulations that have been done up before this point, there's some work done by Juan Soler in his 2013 paper. I think those are Patrick Hennebel's simulations. And smaller, Chen and Ostreicher, this is colliding flow simulations with magnetized media. You get like a magnetic field little parallel there to the filament along which the cores form. And then our data are right there. So that's to scale. In fact, I think it may be even a little too large. So we need something at much, much higher resolution to compare with the ALMA data, and even frankly to compare with the CARMA data. And so in comes Arepo, the package that normally does cosmological simulations. This is work by Philip and Blakeslee Burkhart with the Lars Hernquist group up at Harvard, so I'm working with them. And this is just a slice. Phil will tell you all about this later, just to show you to scale what we're talking about. This is the CARMA data. Here's a shock front, which may well be the origin of this filament along which the 2 cores are forming here. We zoom in and then put the ALMA data. We need to get to higher resolution to really be able to compare with the ALMA scale, but we're getting close, and Phil's doing really great work. So this is some nice work in progress using both cutting-edge observations and simulations. So things are things are pushing forward here. I'm just going to put up a few statements and questions. Things are looking good for the protostellar polarization world. They're, of course, getting incredibly complicated at the really, really high resolutions that the other folks who've got data are probing. But the future is bright, and I'm happy to take your questions. Thanks.
Excellent talk, beautiful data. So I wanted to point out that we found in 2013 in a paper by Chapman that there is some evidence that in some cases for certain kinds of sources you might recover some of the alignment between outflow and magnetic field even on the larger scales. So as you go forward and get more data, it might be interesting to look for trends among different kinds of sources to see whether there is some kind of relationship between fields and outflows that emerges.
Yeah, absolutely. And in fact, I didn't talk about this, but in our paper, in the 2014 paper, we saw that some of the lower polarization fraction sources might actually have had outflows and magnetic fields that were perpendicular. So there are clearly some trends to be investigated that will be probably quickly illuminated once the sample's big enough. Yeah. Yeah, Laura.
Hi, Chat. I was wondering if you have any molecular line data and whether you actually see any evidence of like infalling gas along some of the magnetic.
Excellent question. So yes, we do have molecular line data. Unfortunately, the ones we chose, while very interesting, were basically all outflow contaminated. So we've put in some proposals for ALMA now to see if we can get the right tracer to trace the right scale, the right temperature, and the right density. I think it's going to be a little bit of a crapshoot for the next cycle or two, but we'll get there eventually. That's one of the main reasons we're looking for the simulations now, because we can see what their infall profiles look like long before we're going to be able to see what the actual ones look like in the molecular lines. But that's the next very important goal.
So it seems to me that a slightly larger regions of the magnetic vectors are tracing the pinching on the magnetic field, and slightly more extreme case of hourglass. When you get to the disk, there's rotational supported structure, so the magnetic field lines are actually parallel to the outflows.
That all of these things can be seen in my N of 3 objects here. If you look at all three of those, you can get some kind of hourglass structure if you smear enough. So that may in fact be happening on all of them. It's unclear. But yeah, your comment is on point, and really we won't be able to see the true number of sources that have things that look like hourglasses when you beam smear, and what's happening at very small scales till we get a bigger sample. Yeah. One more? All right, excellent.
I was going to comment what Giles said, but also I was questioning the question. All of your vectors were all the same size.
Yes.
So you clearly didn't mark with relative to percent polarization. But what kind of trend are you seeing in the percent polarization?
The problem, and this is a technical thing that I'll happily talk to you about later, but we recover very different structures in Stokes I and in Stokes Q and U now with the incredible dynamic range and sensitivity of ALMA. So at the peak, the polarization fraction is still a number we can probably believe, but getting out toward the filaments, eventually you're dividing the polarization signal by the noise in the Stokes I map. And so we see a few percent toward the peak, which is consistent with what we believe, but out toward the filaments, you can get kind of unbelievably high numbers. So we have to think better about how to do this in the ALMA era.
Okay, we had 25 minutes on my schedule, but I've been informed that it's only 15, so you're already 5 minutes over. So
Sorry about that.
moving on.